Swayam Prabha. Digital India. Educated India.
Okay, good morning. I'll be talking about some aspect of predicting drying rate more from a theoretical point of view. And to recap what we discussed with regard to drying operation, so there is a requirement for an industrial scale drying of large solid objects which are containing some moisture. And so we said that predicting the equilibrium moisture content for a solid material is very difficult theoretically. So we tend to do a batch drying experiment. We take a small piece of the solid and then we subject this to a drying condition that we wanted in the industrial scale. Okay, we mimic similar kind of air temperature, similar kind of geometry, similar kind of the initial humidity and so on so. And then based on that we get a what is called this drying curve, which is basically measuring the moisture content as a function of time. Okay, so this is called batch drying kinetic data. Batch drying data. And then you will see something like, okay, so the generic feature of a drying batch drying data is something like this. So moisture starts at some initial moisture and then as a function of time this moisture content decreases and reaches some sort of a constant value. Okay, and this constant value is what we say as the equilibrium moisture content. Okay, no matter how long you expose this further, moisture content is not going to decrease. Okay, so that's what we call it as a equilibrium moisture content for this drying condition. Okay, when I say this drying condition, I mean the flow rate of the air, the temperature of the air, the initial humidity and so on. Okay, but if I change the temperature of the air, this may equilibrate at a different moisture content. Okay, so it's a very strong function of the drying condition. And then we said that this is very kind of raw data, and then if I replot this data in terms of drying rate, we find some interesting feature with regard to different drying mechanisms. Drying rate plotted as a function of the moisture content. So we saw something like there is a constant drying flux and then there is a falling rate. Okay, so we call this as a constant rate drying. There can be some initial period which we are ignoring it here, and then there is this other period which we call falling rate. So this humidity at which the transition happens from the constant to falling rate is we call something as critical moisture content. And the point where the drying flux goes to 0, we call this as a equilibrium moisture content, which basically corresponds to this point. So these are some of the generic features. So we can obtain these data from experimental data, okay, drying experimental data, and then now we know up to what moisture content the drying is constant, beyond which there is a falling rate, and based on the different regime we can try to find the time required to dry a larger scale industrial scale drying operation. Okay, so now what we want to ask here is, out of these two regimes, the constant rate and falling rate, is there a way we can theoretically predict the drying rate? So if you think about this falling rate, here we are talking about drying of an bound moisture. Okay, in the falling rate we are talking about drying of bound moisture. So what is bound moisture? Bound moisture refers to water content inside the solid matrix through capillaries, through its microstructure, through some sort of adsorption. Okay, it is internal to the solid object. That's what we call as a bound moisture. The characteristic of a bound moisture is that the vapor pressure exerted by this bound moisture would be lesser than that of pure water at the same temperature. Okay, so this is a definition of bound moisture. So here the drying rate is limited by at what rate this internal moisture is able to reach the surface from the interior. So it has to do with what is the diffusion coefficient of the moisture inside the solid matrix and what is the tortuous path it is available for diffusion. So it is very intricate transport mechanism, okay, and which is what making it very difficult for us to predict theoretically, okay. So prediction of drying rate under the falling rate regime is extremely complicated. That's what we have to rely on experimental data, okay. Now on the other hand, if I look at the constant rate drying, this relates to drying of unbound moisture. What is unbound moisture? Unbound moisture is nothing but water that is covered on the surface, external surface of the solid matter. It forms typically a thin film and it acts like a pure water like property. What I mean by that, the vapor pressure exerted by the unbound moisture is equal to that of pure water, okay. It is as if a thin water layer is evaporating, okay. So here the solid is not playing much of a role, it is not really controlling anything. So in that case, the drying rate is more limited by the gas that is passing over, okay. What is its temperature, how much humidity it can hold, and what is the mass transfer coefficient in the gas phase, okay. Those are the limiting conditions for constant drying. Now if this is the case, then we can understand that the drying property of a gas is something we can write in terms of some mass transfer coefficient, driving force, all the thing that we learned about mass transfer, interface mass transfer, we can apply, and then we can probably hope to predict theoretically the constant drying rate, because here a solid is not limiting, only the vapor phase properties are limiting, the gas phase properties are limiting, okay. And we know how to handle mass transfer coefficients, heat transfer coefficients, driving force, all that we can handle in the gas phase easily. So we are going to look at that opportunity, that possibility, okay, how to theoretically calculate constant drying rate, okay. So that is the main objective of this lecture. So in this regard, I am going to show some simple geometry. So let's say we have a thin drying material, okay. So let's say it has a length of some L and then some width of W and some thickness T, okay, and it has a lot of this unbound moisture, okay. The water forms a thin layer around the surface, and now I am going to send a air for drying this. So this air is represented in terms of its dry bulb temperature Tg, that is the actual temperature, and it may have some initial humidity, and it will flow at certain velocity v, okay. These are all the characteristics, these are all the conditions for drying. When I fix Tg, y, v, I say that this is a constant drying conditions, okay. This constant drying conditions will lead to certain drying pattern. If I change any of this variable, then the drying pattern will also change, okay. So when I keep this constant, I talk about constant drying conditions. Please understand, this is the drying condition from an operation point of view. This is nothing to do with the constant drying rate I was talking about. These are two different things. Here I am talking about constant drying flux, how much water is evaporated per unit area per unit time, okay. That is nothing to do with constant drying conditions. When I say constant drying conditions, I am talking about operational point of view, okay. Whereas this one talks about the transport approach, transport mechanism, and this y here is a humidity. We write this is kg of water over kg of dry air. So when we talk about humidity, we talk about humidity for two cases. One is the humidity of the solid and the humidity of the air, okay. So the water content or the moisture content or the humidity of the solid is expressed with the quantity x, denoted as kg of water by kg of dry solid. Whereas for the gas, we use this symbol Y, capital Y, to denote how much moisture, how much water is present in kilogram of dry air in the absence of any moisture. So that's the convention that we will be using here. So then what we can do is, if you look at this case, that is, we say there is an unbound moisture here on the surface. I can denote that by drawing a small thin film around this, okay. It's like more like a wet solid object. So now how is this evaporation happening? Well, the air is coming with a particular temperature with certain humidity, and there is going to be some heat transfer. Okay, some amount of heat is going to be transferred from the air to the solid, because there is a temperature difference. So the moment you have a temperature difference, there is going to be heat flux, and usually the air temperature is higher than that of the solid, so some amount of heat will come. So now I can find out what is the flux of heat transferred to the solid object. Heat transfer flux. So this is H times Tg minus Ts. So H here is the heat transfer coefficient. Actually, this is the gas phase heat transfer coefficient. Ts is the temperature of the liquid on the drying solid. So let us say that if I know the temperature on the liquid surface, that is Ts, and Tg is the temperature of the air, the temperature difference is Tg minus Ts, and then the heat transfer coefficient is H, then the convective heat transfer rate or heat transfer flux is nothing but H times Tg minus T. So then what is happening on the surface? Well, this heat is absorbed by the liquid, and this heat is used for vaporizing or evaporating the liquid water. Okay, so that should be nothing but mass transfer flux times the latent heat at corresponding to Ts. So heat required for evaporation. And that is equal to we say Nc times lambda S. So here the lambda S is the latent heat of vaporization at temperature Ts. Nc is the constant drying flux. Okay, so here this is where the marriage between the heat transfer and mass transfer happens. Whatever heat that is supplied to the solid, the liquid on the solid basically absorbs it, and equivalent amount of water is now evaporated. Okay, so you can imagine there could be a steady state where the incoming heat is used for evaporation. Okay, now I can match these two heat fluxes. So we have Nc lambda S is equal to H times Tg minus Ts. So this is one equation that we say that the heat required for evaporation is basically supplied by the convective heat transfer from the gas. And then we can independently also write the constant heat transfer, constant mass transfer flux as Ky times Ys minus Y. This is equation 2. When I talked about the constant drying flux in the last class, I mentioned why Nc can be constant, because the drying conditions are fixed, so that the mass transfer coefficient Ky will always be fixed, and then this initial humidity is also fixed and it is passing by, and then Ys is the saturation humidity corresponding to the liquid surface temperature. So by equation 1, I am saying that there is a steady state at which the heat balances between the convective heat transfer and evaporative heat transfer. Therefore, the Ts will have to reach a constant value. Therefore, the mass transfer flux Nc also reaches constant value. So these are basically the two equations that allows us to predict what is this Nc is. So if you look at this Nc, the only thing that we do not know is the saturation humidity, because the saturation humidity has to come from corresponding to the temperature Ts. But you can use this equation 1 to solve for Ts. Okay, Ts and Ts is something, so what I can also do, so let me write, let's combine 1 and 2. So then I have ky times ys minus y is equal to h by lambda s times Tg minus Ts. So this is equation 3. Now from this equation 3, we can obtain Ts and Ys using psychometric charts. As I said before, since we have not talked about humidification, Ts and Ys will be, let us say, given or known. Okay. Once we know Ts and Ys, we can use equation 2 to find the constant drying flux, which is Nc. So equation 2 gives the theoretical estimation of Nc, which is constant drying flux, constant drying rate. By knowing Ts and Ys from equation 3. Now the next objective is, looking at this equation 2, we can look at correlations for the heat transfer coefficients and mass transfer coefficients and etc., because we have we know how to find the correlations, and the use of such correlation is the following, that this Nc constant drying rate is for a given drying conditions. Okay. Now let us say I change the flow velocity. Okay. So if I change the flow velocity, do I have to again do this experiment all over, or can I make a prediction extrapolation from the known data? Okay. Or if I change the initial humidity, or if I change the dry bulb temperature Tg, can I use one single experimental data and then from there extrapolate what would happen if I change the drying conditions? Okay. So that is a question we want to answer. To answer that question, all that we need to look at is, we look at this equation 2, we find out what would happen if I change the drying velocity or the temperature of the drying gas or the humidity itself. Okay. So that is the context. And one more thing you can also see is that if you look at this equation 1 and equation 2, the correlations available for heat transfer is actually far more than that of mass transfer coefficients. So by looking at equation 1 and 2, I can find how Nc will change with respect to all the drying conditions by looking at how H will change with respect to those conditions, or equally I can look at also this mass transfer coefficient and I see how those going to change. So I can use either heat transfer correlations or I can use mass transfer correlations, because Nc is after all related by these two equations. Okay. So now what I am going to do is, I am going to look at some empirical correlations for heat transfer coefficient as well as mass transfer coefficient, and then I predict how Nc will change if I change the drying conditions. Okay. And then when we do that, we also have to specify what is the drying conditions is going to be. Okay. For example, let us say I take case 1 where I say that the drying is flow of air parallel to a flat surface. Suppose if you have a drying condition where you have a solid substrate and then the air is actually flowing past to it. Okay. So that is a parallel flow. So in that case, we can find that the Chilton-Colburn analogy JH and JD, these are actually equal quantities, is given by something like 0.664 Reynolds number to the power minus 0.5. Okay, this is one of the correlations applicable for flow of a fluid parallel to a flat surface. So here you can see this JD factor is common for both heat transfer as well as for the mass transfer. Okay. So here JH, let's take the heat transfer approach. This is given by H by G D, this is going to be Cp, Prandtl number to the power 2/3, and that is equal to 0.664 Re power minus 0.5. So now if you remember, this JH is defined as Stanton number times Prandtl number power 2/3, and the Stanton number is written as Nusselt number over Reynolds number times Prandtl number. Now if I substitute all these Nusselt number, Prandtl number and Reynolds number, you will get this group of terms, and that must be equal to this. So what we are saying is, from this relation we can write H is equal to 0.664 Re power minus 0.5 G Cp by Prandtl number 2/3. So this basically tells how heat transfer coefficient is going to change with respect to drying conditions, as well as the property of the drying medium, that is air. If you look at let's say if you have air at this is an example calculation I have done. Let's say if you look at air at 95 degrees Celsius, at this particular conditions we know what is the viscosity, density, heat capacity, etc., all that can be plugged in here, and then we can show H is proportional to or equal to 3.95 G by Te power 0.5. So here G is nothing but velocity, flow velocity times the density. So basically it's a mass velocity, and D is a characteristic space, the dimension of linear dimension for which the gas can flow through. Okay, so it is related to some sort of length scale. And what is important to note here is that H is proportional to square root of flow velocity. So H is proportional to square root of flow velocity, and you can see that NC from this equation 1 that I showed before, if you look here, this NC is proportional to H, keeping all the other thing constant. Let's say if you say NC is proportional to H, therefore it is proportional to the velocity of the flowing stream. So what it means is that suppose if I do an experiment at certain conditions and I find what is the constant drying rate. Okay, so that is our basis. Now I want to calculate the drying flux for another situation where I might increase the flow velocity by 50%, or I might just double it. In that case, I can use these correlations to find how would I have to recalibrate my constant drying rate. It's going to be proportional to the square root of the velocity. Okay, so if I just make a double of the flow velocity, NC will be square root of 2. Okay, it's going to be some 41% more than the previous. Okay, so that is a big use of this kind of analysis. Similarly, let's say you are not changing the flow velocity, you are changing only the temperature. Okay, so we know that NC is proportional to Tg minus Ts. So it is going to be proportional to the difference between Tg minus Ts. If I increase Tg by 10 degrees or 20 degrees, proportionally NC is going to change. And then similarly, if I change the initial humidity, this is also proportional to the difference in the humidity. Okay, so all this analysis basically helps us to find out how the constant drying rate will scale or change when I change the drying conditions, if I know those values for one particular basis conditions. Okay, so that's the main use of these correlations. So all this thing has to be applied only if the flow is parallel to the flat surface. Suppose if the flow is perpendicular to this drying solid, then all this correlation will change, all this dependence of NC will change. Okay, for example, just for comparison, I have one for perpendicular flow. So let's say that air flowing perpendicular to the solid. So in this case, you will see the heat transfer coefficient is given by something like 24.2 g power 0.37, sorry 3.37. So this has to be compared with the parallel flow, where H was proportional to g power 0.5. So from here you can see that which flow is more preferred, parallel flow or cross flow, perpendicular flow or parallel flow, because parallel flow is actually proportional to g power 0.5. It actually increases much better than in a perpendicular flow. Okay, so if you are trying to dry a wet cloth, wet towel in your room, you can see the flow pattern makes a big difference whether you want to send the flow parallel to it or perpendicular to it. Okay, so that is a lot. You can actually extend this analysis even beyond. Right now we are talking about only the flow velocity, but you can also do the same thing with respect to the initial temperature, initial humidity, and then change the drying conditions, etc., etc. Okay, but whatever it is all possible only for constant drying conditions only. So how do we handle the falling rate? Okay, so as far as the textbook is concerned, so there is no much of a theoretical description about falling rate predictions, but there is a lot of research happening in that area. That is still an active field, because if you look at let's say you're all doing let's say chemical reaction engineering, you're talking about heterogeneous catalysis. So you have a packed bed, and the packed bed contains catalyst or solid particle, and the gas, the reactant will have to diffuse through in and then react at the interior, and then the product will have to diffuse out. And then to look at this internal mass transfer, you define what is called something called Thiele modulus, which kind of tells you the relationship between the diffusivity and reaction rate constants. In a way, you can also treat this problem of falling rate in a very similar sense, that if you have a drying material that is granular, let's say you have a solid particle that are granular, and then you want to dry that, you can also write a diffusion equation for a spherical particle, and then you look at what is the initial moisture is and what's the rate of moisture that is coming out because of evaporation. You can treat very similar to heterogeneous catalysis, but for a drying operation. Here there is no reaction, it's only diffusion control evaporation, and such treatment is not there in the textbook as far I have seen, but that's something that one can try that as a project if you like. Okay, so it's kind of a nice combination between the heat transfer theory to reaction engineering theory to mass transfer also. Okay, so that's all I have to say about the drying, and in the next few classes I will do some tutorials, some problems related to these calculations. Yeah, so basically if you look at this, the temperature sensitivity of the coefficients are not very high, but the driving forces are. Okay, so you could say that if the temperatures change, you can recalculate your coefficients. However, the major component will be the temperature difference being the driving force that will impact NC a lot more than the coefficients itself. Yes, yes. Other things will not change. Yeah, the driving forces are the same. That's a good point. That's a good point. Let me just elaborate there. So there are two things I neglected. One is this initial condition. So what that is let's say initially the liquid surface temperature is Ti, and then because of the balance between the heat transfer rate and mass transfer rate, and at steady state the liquid will reach a Ts temperature. Now between Ts and Ti, if that difference is not very much, okay, then this period will be very short. On the other hand, if you are starting with a very cold object, okay, and then the time that it reaches from the initial temperature Ti to the surface temperature, that period can be quite long. Okay, but here in this analysis we have assumed that the initial temperature of the solid is very close to Ts, so the time required is not very much. That is one assumption. The other assumption is that if you look at this liquid that is evaporating, it is evaporating at Ts and going into the air stream, but air is flowing at Tg. So this moisture has to be heated by sensible heat from Ts to Tg, and that would be Cp times Tg minus Ts. That sensible heat also I have ignored, because if you look at the total heat requirement, the latent heat requirement is far more comparable to the sensible heat. So I have assumed that to be also negligible, which means Tg and Ts are very close to each other. Okay, but these are all assumptions. But like I said, you can extend this theory to even more sophisticated conditions. But like this is a UG class, so we want to keep it as simple as possible. Okay, by making these assumptions. I'm not saying equal. I'm saying something close by. That assumption is not correct. So I'm not saying Tg and Ts should be close, because then I have basically a very long drying period. But what I'm saying there is, even if Tg and Ts are quite different, but the sensible heat required to heat the vapor from Ts to Tg is going to be comparably lesser compared to the latent heat required for evaporation. So there the reason for assumption, that assumption is different than the other assumption. Okay.